Okay, our chapter today will be discussing matrices for size change. And in doing that, it should sound a little familiar from geometry. You're going to recognize different relationships between figures and the size changes. We will relate size change to matrices and vice versa, and then we're also going to be able to graph figures that have examples of this. But before we start with the actual size change, let's review something from 4.3 that was in the homework. The identity matrix is going to be huge. The identity matrix was a 2x2 matrix. It was the ordered pairs 1, 0, and 0, 1. So if you look at those two ordered pairs, 1, 0, 0, 1, and wrote them in point matrix form, which would be 1, 0 going down, 0, 1, because we learned that a point matrix by itself, a single point, would be listed x over y. So our ordered pairs are 1, 0, 0, 1. And when you look at those 2 points on a graph, they are basically the points in red and blue seen here. So 1, 0 is in red, 0, 1 is in blue. Those points will be the points we use from here to the end of the chapter to move on our coordinate plane. The identity matrix is key. It's like the basics for all the rest of the matrices. It's the starting point, think of it as. And we're going to start on a little list here, and our list starts with the identity matrix, but our list will contain about 10 of these by the time we're done, based on the different transformations we're going to do. We'll start that list today because we're going to talk about size changes. So knowing that, let's move forward. A size change you read about was a new symbol, capital S sub k, where k is called the magnitude. You learned that in geometry. And k cannot be 0, because if you say what is the size change and it's 0, it's not going to work. If k equals 1, the shape stays the same. If k is greater than 1, the shape will increase in size or grow. And if k is between 0 and 1, the shape decreases. So a typical situation would be if we had our rectangle, and let's just fill it with some color here. Okay, so if we had our rectangle now and we wanted to take it through a size change that was a positive value, that original positive value would now make it a bigger situation. And so our graph, when you look at the two shapes, the original shapes, we could do it and take this shape, and if I now said let's take that black one and let's take it through a size change again that's bigger than 1, and it might end up like that. So now if you look at those two shapes, the red versus the black, the red being the original, we can say, well, a couple different things. What do you notice? Most people would say, well, it looks like they stay the same shape. True statement. They're both rectangles. The angles are preserved is a good statement. The edges are parallel. You could say not all edges, but you could say the corresponding edges are parallel. And you can do that same thing in the other direction. So let's reset. Let's take our black triangle here and let's make it smaller. And so we would have been moving it to something less than 1. So if we did that, less than 1 but bigger than 0. So now if I would have used a size change factor, less than 1 but bigger than 0, I might now have that black triangle, which it looks to be, maybe a half, third, a fourth, it could be anything in that range. But again, look at the two pictures. What happens to the original shape compared to the new shape? The shape doesn't change. The angles are preserved. The edge lengths are not. So these are characteristics we're expecting you to look at. list some of those characteristics that would happen for all shapes. We will be talking about that list as we move forward, but start off with things like we just said. The shape stays the same. Talk about the angles, talk about the edges. That's what some of your other characteristics would be. We want to list when you come to class, so make sure you have it in your notes, and we will then discuss it and see what we agree with. So, what are the characteristics of a size change taking place? Now, from here, we know that the identity matrix is 1, 0, 0, 1. If we would take that identity matrix and multiply it by the point matrix, xy, and right away we're saying, well, wait a minute. This is a 2 by 2. Our point matrix is a 2 by 1. So when we finish, yes, we can multiply because our inner numbers match. And then we look at the outer numbers, and that's a 2 by 1. So we know we're getting a 2 by 1 here. So if we want to multiply that by these two, it's easier. It's one of the easier ones in your head because you don't have big numbers. So here we go. 1 times x is x. 0 times y is 0. 1x plus 0 is x. Now to do the same thing on the second row, first column multiplication. 0 times x is 0. 1 times y is y. 0 plus y is y. So when we multiply the identity matrix times any point matrix, xy, you should get back to what you started with. That's why it's called the identity matrix. Now, let's take the K0, 0K matrix, which you should know as our size change matrix, and multiply it by any point. So what happens to any point if we take it through a size change of K? Again, K times x is Kx. 0 times y is 0. Kx plus 0 is Kx. Second multiplication would be second row, first column. 0 times x is 0. K times y is ky. Added together, we get ky. So we're getting that kx, ky matrix. So notice our first name in our list of things. The name is a size change. The notation is s sub k. The matrix we use is K0, 0K. And the xy shortcut could be, if I have any ordered pair xy, and I take it through a size change, I will get a kx, ky ordered pair, which means all I have to do is change the ordered pair. So let's do this with some actual numbers. If we look up here, and we say we want you to take these points through a scale change of 3, we just learned all you have to do is multiply each x and each y. So 4 times 3 is 12, 1 times 3 is 3. New point, negative 4 times 3 is negative 12, 0 times 3 is 0. New point, negative 5 times 3 is negative 15, negative 2 times 3 is negative 6. We have 3 new points that have gone through a scale change, and look how you would write them in matrix form. The ordered pairs 4, 1 go down, negative 4, 0, 5, negative 2. So xy ordered pair listed down, and if we apply a size change of 3 to them, the resulting matrix, 12, 3, negative 12, 0, negative 15, negative 6, is the actual change to those points when it goes through that size change. So if you look at this one, what size change do we have going on? We have the original points 4, 1, negative 4, 0, negative 5, negative 2. If you know your scale change, you would just multiply each original point times that k value that it represents the magnitude of change, and you would get your new ordered pair. The whole moral of the story is there is no need to multiply. You should not have to do this long multiplication process with your matrices for a size change. Okay, this is for size change. You may have to do some multiplication later on, but on a size change, we now have this shortcut that says you can do kx, ky. So with that, you should be able to work on our problems, use some of the shortcuts, be able to graph points. I think you'll be good to go for all size changes using matrix notation.